A very good day to my beloved lecturer, Dr. Rosita Omar. Well, my name is Ivan Anaraki Rajendran. My metric number is 188024. We are from Team Bond. So today, I and my team members going to present about manufacturing of sugar from sugar beet. So, first of all, let me introduce all my team members. Firstly, I myself, Ivan, and the second, Nurul Atika binti Muhammad, and the third one, Nur Azmin binti Abdul Rashid, and the fourth one, Nur Amira Shafika binti Wan Mahmud. Okay, for this semester, we have add on four new unit operations, which are crystallization, centrifugation, dryer, and also boiler. So for this semester, we have calculated all the material balance for these four new unit operation. We also have calculated the energy balance for all the unit operation that are used in this project. So let us go deep about for each unit operation that we used in this project. Okay, let us move to the next unit operation, which is mixer. So inside this mixture, the CO2 will be added on to the mixture, and then the sugar solution will be mixed inside the mixer with the CO2. So basically the sugar solution is concentrated as a precursor step to avoid any reaction of sugar solution with CO2 in the clarifier. So let us move quickly to the Excel. This is the Excel that we have calculated for the mixer. So mixer, basically there are three streams inside the mixer. Firstly, there are two inputs and then one output. So the input it will be stream number 6, stream number 9, and stream number 10 is the output. And then the stream number 6, which is input, is 70 degrees Celsius. Stream number 9 is the input of the CO2 is 25 degrees Celsius. Stream number 10 is the output will be 60 degrees Celsius. Okay, let us go to the energy balance calculation of this mixer. So basically the reference temperature is 25 degrees Celsius. So for water, sucrose, non-sucrose, and beet marks. So for this mixer, we have calculate the flow rate for each stream. So these are the flow rate for the stream. So basically, this is the flow rate, and then we have calculated the enthalpy, specific enthalpy. So by multiply the flow rate, mole flow rate, and also specific enthalpy, we will get the enthalpy rate. So and then we must do for each stream. We have three streams here. For each stream we have to do, and then we will add up the total enthalpy for each streams. So the output stream of the enthalpy rate minus with the input stream of the enthalpy rate. So we will get the Q. So Q we get here is kilojoule per hour, and then the final here is kilowatt per hour. So 10,829.5692 kilowatt per hour. Thank you.
Okay, I will continue with the clarifier. The function of clarifier is to remove as much as possible the non-sugar component and improve the clarity and transparency of the juice. And we use CO2 as it is lower in cost. So this is our material balance. The temperature for the input is 60 degrees Celsius and the temperature output is 80 degrees Celsius, and the pressure, both of the pressure input and output is the same, which is 2 atm. So we got the mass flow rate for input is 1974.2183 kilogram per hour, and for the output is 1774.8456 kilogram per hour. And this is our energy balance. We divided it by 2, which is energy balance with non-reactive species and energy balance with reactive species. So we choose reference H2O sucrose non-sucrose beet mark at 25 degrees Celsius. So we do the calculation of energy balance. We do as usual, which is Q equals to delta H, because we assume that EK, EP, and WS equals to 0. So we got Q equals to delta H, which is summation NH output minus summation NH input. And we calculate it, and we got 145622.0214 kilojoule per hour. And for the energy balance for reactive species, which is reaction with CaOH2 plus CO2 that produce CaCO3 plus H2O. So we use the heat formation method that we have to calculate the squiggle first and delta HR, because we have to plus with the summation with the delta H. So the equation is Q equals to squiggle delta HR plus summation of NH output minus summation of NH input. So we got Q equals to 410,624.3363 kilojoule per hour.
Okay, for the filter, the function of filter is to remove non-sugar component in the solution, as well as to improve the transparency of the juice. So this is our filter here, and the temperature in is 80 degrees Celsius, and the temperature out for both is 70 degrees Celsius. And this is our energy balance. This filter release energy because the Q is negative, which is negative 87.3538 kilowatt. Okay.
Assalamualaikum and a very good evening. My name is Norazin binti Abdul Rasid. So I will continue for heater part. Heater is the equipment that we put before evaporator and after filterization. The main objective to put the heater before evaporation is to preheat the sucrose juice before entering the evaporator. This is because we know that the temperature inlet for evaporator is a very high temperature. So heater is a must equipment that we have to put before evaporator. So the energy produced by the heater is 18.19 kilowatt. So I will show you how we will get this value. Okay, this is the calculation for heater. As you can see, the inlet temperature is 70. It's quite high. This is because from the clarifier, the temperature outlet is already very high. So after it pass filter, it's literally like reduced to 10 degrees Celsius. And then from the heater, we will increase the temperature by 10 degrees Celsius, which is from 70 become 80 degrees Celsius. And heater works at constant pressure. So the calculation is quite easier. It's quite easy because we work at constant pressure. Okay, as you can see that we choose the reference state for sucrose, water, non-sucrose, which is potassium, is at 25 degrees Celsius and 1 atm. So that we assume the energy, potential energy, the kinetic energy, and the shelf work is equal to 0. So after that, we will get the Q equal to H out minus H in. So there. So I will show you the calculation, which is here. As you can see that we will pick the value of the CP 75.4 kilojoule per kilomole degree Celsius. We will minus the temperature inlet minus with the reference. Same goes like the calculation for outlet, which is the CP we will times with the temperature outlet minus with the temperature reference. So we will get the total of the value from the out times with the number of mole. So we get the kilojoule per hour, and we minus with the inlet as the same steps. So we will get the Q. So after that, we get the value for in unit kilojoule per hour, right? So we will change the value, which we will divide by 3,600. seconds, so we will get the unit in kilowatt. Okay, that's all for heater calculation. Thank you.
Okay, for the evaporator, evaporation is a process to remove most of the water. It concentrates the clarified juice to a thick syrup of about 65 bricks. So this is our calculation for material balance, and we got the mass flow rate for input is 1774.6750 kg per hour, and for the output we got 668.4028 kg per hour. And the temperature input that we have searched is 80 degrees Celsius, and for the output is 90 degrees Celsius, and both pressure are the same, which is 1.2 atm. For the steam, the temperature is the steam input is 130 degrees Celsius, and the output for the steam is 100 degrees Celsius. For energy balance, we have calculated Q equals to delta H because we assume that EK, EP, and WS equals to 0. So we got Q equals to delta H, which is NH output minus summation NH input. And we calculate, we got 725.161192 kilowatt.
Okay, let us go to the next unit operation, which is boiler. So this boiler basically is used to produce steam that could use to evaporator, which need the steam to evaporate the water out. So the bagasse is recycled to this boiler to burn and eat the water liquid to the steam. So let us go to the boiler here. So this is the boiler have 4 stream, so which is 2 streams will be input and 2 stream will be output. So the water will input to the boiler, where the bagasses will input also into the boiler. The bagasses will be burnt to supply the heat to boil the water, so the water become the steam here. So the bagasses will burn and produce the fuel gas. So we have done the material balance calculation here. So the temperature input is 25 degrees for both steam, 30 and 32. So the temperature output is water is under 30 degree and fuel gas is under 30 degrees or so. So so the energy balance, we have calculated the boiling point here of the water and the HV of the water. Okay. The energy balance here, the water at 25 degrees Celsius is specific heat is under 4.86. The water at 100 degrees Celsius, the specific heat is 419.06, and the water at under 30 degrees Celsius is under 25.68. So we could find out the Q here is when we minus uh, when we times, so we will get Q this one, and then when we convert to the kilowatt, we will get 685.231 kilowatt.
Hi, me again. So we continue for centrifuge part. For centrifuge, others known as separator is the same thing. So for the centrifuge, the main objective of centrifuge is to separate the molasses from the crystallized sugar. So the work shaft is 15 kilowatt and the energy produced by the centrifuge is 10.85 kilowatt. So I will show you how we will get that value. Okay, here the calculation for the separator. As you can see that we work at a very high pressure, which is the inlet is quite low, less than 1 atm, and the outlet pressure is quite high, which is 25 atm. But we work at a quite different temperature, which is the inlet temperature is 70 and the outlet temperature is 60 degrees Celsius. So the calculation for this part is quite different from others. So we will consider to get the specific enthalpy, we have to consider the pressure difference. So to calculate that, we will use the total of enthalpy, specific enthalpy equal to delta P times specific volume plus with the what is that we call that plus the CP value. So that here I will show you the calculation, how is it done. To get the specific volume, we have to deal with the specific with the SG value. So that here I will just calculate from the manually, so we get 0.018 for water. So I will just times with the pressure difference. Here pressure difference, which is 0.74 minus 1, because the reference step for sucrose, water and no sucrose, which is potassium, is at 25 degrees Celsius and 1 atm. So we just plus with the CP value times with the different temperature from the outlet to the reference. So same as other calculation, which is this one and this one, same. As you can see there, is same. Okay. Same goes as for the outlet. So as I can say, for separator it has chef work. So we use the power from the machine as a chef work, which is 15 kilowatt. We have to change it to kilojoule per hour in order to plus it, so that the Q value that we get is delta H, delta enthalpy, plus with chef work. We assume the energy, potential energy and kinetic energy equal to 0. But as we have the motion inside the machine, so we cannot assume the work chef as 0. We get the value, so we just add it. To get the enthalpy, we just the Hn, which is the enthalpy out minus the enthalpy in. So we get the value of enthalpy, delta H, so that we just plus with the chef work. Okay. Yeah, this one. This is final value, so we have to change the unit, so we get the in kilowatt. So this is the final energy produced by the separator. Okay, that's all for centrifuge. Thank you.
Okay, for dryer, the function of dryer, the drum dryer is used for sugar beet pulp drying, of which some of the water was preliminary pressed out to the level 88 to 90% of dry matter. So this is our material balance. We have calculate, and we got the input is 272.0872 kilogram per hour, and the output that we have been calculated is 244.8032 kg per hour, and the temperature the input at the temperature at the input is 60 degrees Celsius and the output is 55 degrees Celsius. So we do the energy balance based on the temperature, because we assume that the pressure input and output is the same. So this is the energy balance. We assume EK, EP and WS is equals to 0. So we got Q equals to delta H, which is summation NH output minus summation NH input. So we calculate, we got Q equals to negative 0.411216086 kilowatt. So this is our enthalpy, heat enthalpy, and this is our energy.
Crystallizer is one of the most important process in this sugar processing. Crystallizer used in industry to achieve liquid solid separations to remove unwanted substance. This crystallizer capable of generating high purities product with a relatively low energy input. Okay, and this is our crystallizer. The temperature in is 65 degrees Celsius and the temperature out is 80 degrees Celsius at a constant pressure. This crystallizer is exothermic that release negative 10.36 kilowatt, and this is our energy balance. this heat in, and this is the heat out. So we will get this exothermic crystallizer. Okay, for the costing of our project, this is our total equipment cost. We choose the best one so that it will fulfill our requirement of our project, and also affordable for us. And look at this price. The price is cheaper. Okay, for the raw material, we have sugar beet, carbon dioxide, and also calcium oxide, which is the total cost is here. And for the utilities is based on our electricity use and also the sugar, not and also the water. So the total here. Okay, for the fixed cost that we have to pay every year is for the maintenance, for the labor, plant overhead and laboratory, and also the capital charge. And the total here. Okay, for our cash flow chart, we does not gain any profit for the first 3 years, and for the next year we continuously getting profit because we could sell the sugar well.